So chapter 3, lesson 4. Today we're going to talk about proofs with perpendicular lines. So the first thing we're going to talk about, though, is the distance from a point to a line. And the distance from a point to a line is going to be the length of the perpendicular segment from the point to the line. It's always going to be, that perpendicular distance is always going to be the shortest distance between the point and the line. So for example, if I asked you to find the distance from point A here to line K, the shortest distance is going to be this perpendicular segment. And you'll look for the right angle. Technically, I could draw a segment and say, well, A could get to point K by drawing a line segment here, but it will not be the shortest. So whenever they ask you for the distance from a point to a line, you're going to always use the perpendicular segment to calculate that distance. Think about it like this. Let's say I have some banks, the banks of a river. So this is the water, and this water is full of alligators. And you want to swim across this lake or this river the fastest way possible. So you're standing here, this is your point. The fastest way to get across this river is going to be the perpendicular distance. You would not want to try to swim from, say, over here to over here. That would take a lot longer to swim across that river. So just remember, the shortest distance is going to be the perpendicular segment. So when I give you a picture, I'm going to be giving you several different segments with some ordered pairs attached. You're going to look for the perpendicular segment and calculate the distance or the length of that segment. And that's what we're going to do in the next example. So for the next example, we're bringing back our distance formula because our segments will be graphed on a coordinate plane, or I will give you ordered pairs for that. So let's go ahead and try to remember what our distance formula is. So the distance formula, back from the beginning of the year, is going to be x2 minus x1 squared plus y2 minus y1 squared, and it's all under the square root. Now, when you're doing this on the test on Tuesday, you're going to leave your answer in simplest radical form. Tonight, when you do the homework, Big Ideas is going to expect you to put your answer as a decimal rounded to the tens place. So in your work for this question, you're going to show me the work, and on your work, you'll have the simplest radical form, but then you're going to pull out your calculator and then hit the square root button and then figure out what the square root is, rounded to the tens place. So I'll show you an example on this one, how we can round it to the tens place. So here it wants us to find the distance from point A to line BD. So point A is right here. It's this point. And they want us to find the distance to this line. Notice I've got 3 segments coming out of that point. I've got segment here, AD. I've got segment AC with the right angle. This is the one we want to use. And then we also have segment AB. On the test, I'm not going to tell you which one to do. You need to know by that prior slide that the distance is always the perpendicular segment. So the 2 ordered pairs that I'm going to use for my distance formula are going to be ordered pair A, which is -3, +3, and C, +1, -1. If you were to calculate the distance between A to D, you will get this question wrong because it's always the perpendicular segment. Now, I'm going to go ahead and label my ordered pairs. It doesn't matter which one you call ordered pair number 1, which one's ordered pair number 2. I'll just say A is my x1, y1, and C will be my x2, y2. You could reverse it, it doesn't matter. Now I'm going to take those ordered pairs and I'm going to plug them into the formula. So I'm going to do 1 minus -3 squared plus -1 minus 3 squared. So I plugged in all of my ordered pairs, and now I need to use my integer rules. So this is actually going to become -1 plus 3. So this will become 4 squared. -1 minus 3 is -4. And again, this is all under the radical. I need to square them. I need to add them. Now we're going to break it down. We need to do a factor tree for 32. Let me do it over here to the side. Now, it doesn't matter what you start with. If you're really good at finding factors that are perfect squares, for example, if I do 16 times 2 and I recognize 16 is a perfect square, I could go right to my answer. However, let's say instead you decided, well, I know that 4 times 8 is 32. Then here, you might want to go all the way down to prime. Again, you could have also taken the 16 times 2 down to prime as well. Again, whatever you're more comfortable doing. I like to keep writing my primes all the way down so I don't forget about anything. Once I have all prime numbers, now I look for the pairs. Pair of 2s, 1 comes out. I can make another pair. This guy doesn't have anybody to pair with. He stays underneath. Everything that paired up gets multiplied back. So in simplest radical form, whether you did 16 times 2 or 4 times 8, you still get the same answer, and it's 4 square root of 2. So on the test, this is what I would look for. Tonight in the homework, they're going to say, round your answer to the tens place. So you'll do 32, hit the square root button, and this ends up giving you 5.65 rounded, and it keeps going, 5.6568, keeps going. I'm going to round to the tens place. So you would enter, if this is your big ideas homework, you're going to say 5.7 in tonight's homework. On your work, though, you're going to show me all of this. Yes. On the test, you're going to leave your answer like that. So no calculator for the test.
Wait, how did you get that again?
Which one? The 4 radical 2?
No, the 5.7.
Oh, so what I'm going to do is I take out my handy dandy. So the distance from point A to line BD, if it's left in simplest radical form, and this is what you'll put on the test, is going to be 4 square root 2. In tonight's homework, you're going to tell me, you would do the square root using your calculator, and you would tell me it's 5.7. All right, next is the definition of a perpendicular bisector. So the perpendicular bisector of this line segment PQ is going to be line N with the following 2 properties. N is, first of all, perpendicular to PQ, and N is also going to pass through the midpoint of PQ. Remember, a bisector is going to split the segment into 2 congruent parts. But what makes this segment, or this line N, the perpendicular bisector is it's got that right angle there. So again, things you're going to look for are the congruency marks telling us that M is the midpoint. And then we're also going to make sure that it is perpendicular, and we're going to look for the little right angle mark. And that's how I can tell that this is actually a perpendicular bisector versus just a regular bisector. So probably back in the other lesson, if we had PQ here, and let's say we had point M here in the middle, and even if they had the congruency marks, if this segment or the line N that went through here, if it doesn't have the right angle marks, it's just a bisector. It's not a perpendicular bisector. What makes it perpendicular is the right angle mark here. This picture that's drawn here, this is not a perpendicular bisector, it's just a bisector. All right, let's go on. Proving theorems about perpendicular lines. So here's our first theorem. It's called the linear pair perpendicular theorem. And this one states if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if you think about it, if you have a linear pair, we know a linear pair is supplement by the linear pair postulate. If I take that supplementary, the 180, and I divide it by 2, that tells me each of the angles, 1 and 2 here, are going to be right angles in order for them to be congruent. And then as soon as I see I have a right angle there at that intersection, I know that these lines are perpendicular. So as soon as you are told that the two angles in your linear pair are congruent, then you know that the lines were perpendicular. So again, we could have a linear pair. And again, it could be broken here by point G. But let's say this angle was 110 and this one was 70. Notice this is a linear pair because 110 plus 70 are supplements. However, these are not congruent angles. So this is not forming perpendicular lines. So this is an example of a linear pair, but they're not forming perpendicular lines. So in order for the lines to be perpendicular, that linear pair has to have two congruent angles. Okay, the next one is called the perpendicular transversal theorem. And what this one states that in a plane, if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other line. So here, they're going to start out by giving you that you have two parallel lines. And then if one of them is perpendicular to one of the parallel lines, then we also know that that transversal is also perpendicular to the other line that was parallel. If you think about it, we've got corresponding angles going on here. So if these are parallel, then this angle is congruent to this one. So if this one's 90, so is this one. All going to be linked together, recognizing these congruent angle pairs. We also have the alternate exterior one over here too, which would also be 90. Now I realize these theorems that you're going to be seeing, the next one as well, a lot of the words are the same. You just got to watch the order on what's given and what's not. So the next one is called lines perpendicular to a transversal theorem. So here, they're starting out by telling us in a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So if M is perpendicular to P and N is perpendicular to P, then M is parallel to N. So again, same idea here. Notice these angles here are congruent, and notice their corresponding angles. So because I do have a pair of corresponding angles that are congruent, I can use my converse and state that M is parallel to N. But here, as soon as they tell you that M is perpendicular to P and N is perpendicular to P, if they're perpendicular to the same line, then those two lines are parallel. So next one is a layout of a neighborhood. So it's like an aerial photo here. Now, it's got some lines here. If you zoom in, you can probably see them a little bit clearer. So at the end of the line, there's a little red S. So this is line S, and maybe I'll just write it on the outside of the picture. So line S is here. Line T is here. U is here. This is line P and line Q. So they want us to determine which lines, if any, must be parallel in the diagram. So what we're going to use is the theorems that we just learned. Notice in my picture here, I've got a bunch of right angles. So I got a right angle right here. Let's see if a different color will show up better. Maybe the pink. So I got a right angle right there, and another one right here, and another one right here. So what I could state here is that since lines P and Q are both perpendicular to S, right here because of these right angles, I could state that by the lines perpendicular to a transversal theorem, P is going to be parallel to Q. So let me write that in words. So lines, let's see if yellow shows up better, P and Q are both perpendicular to S. So by using the lines perpendicular to a transversal theorem, I could state that P is parallel to Q. And then I got one other pair. I could also say that both S and T are perpendicular to Q. So by the same theorem, the lines perpendicular to a transversal theorem, I could state that S is parallel to T. So let me go ahead and write that down. So lines S and T are both perpendicular to line Q. And again, so by the lines perpendicular to a transversal, theorem, I can conclude that S is parallel to T. So I've got these two markings right here showing that they are perpendicular to line Q. So then I could state that those two lines where the right angles are parallel. Yes. From the photo, I could state that P is parallel to Q and S is parallel to T, and I'm using the same theorem for both. This is what I can conclude from my picture here. So that is it for the notes. Again, for your homework tonight, only a few of the questions will need work. A lot of them, there's a proof. You're going to drag and drop the boxes. Definitely for the distance formula. There's another question where you're going to set up an algebraic equation. And I think there's one other one where maybe you might have to do some adding and subtracting of some simple numbers. But for the most part, it's applications of these theorems. So that is it.